Hi, welcome to series of lectures on electronic devices and circuit subject. I am Dr. Satish Kumar, Professor, EC Department, is Family. Right, we move on to the first topic in PN junction diode. That is open circuit. See, PN junction diode is one of the base devices. If you understand the operation of PN junction diode, it means you can understand the operation of all other electronic devices. Why? Because all electronic devices in this world are made up of PN diode only. Could it be PN diode or Zener diode or tunnel diode or BJT or JFET, MOSFET, UJT, SCR, diac, triac, LED, pin diode, what not. All electronic devices in this world are made up of PN diode only. For example, this PN diode, Zener diode, tunnel diode, all the three are two-terminal devices. The only difference among them is doping concentration. BJT can be assumed as two PN diodes connected back to back in series. So all devices, all electronic devices in this world are made up of PN diode. So to understand the operation of any other electronic device, first of all we should understand the operation of PN diode. In this discussion we start with open circuited PN diode. If any student has a doubt, please post your doubt in the live chat. Now and then I look at the queries and then give you the response. First of all, we move on to construction. An intrinsic semiconductor bar made up of either silicon or germanium is considered. It has, say, a length of L and cross-sectional area A. Into it at one side, donor impurities are added, making it N-type. At the other side, acceptor impurities are added, making it P-type. Two metallic contacts are pulled out from either ends. This central dotted line is an imaginary line drawn for explanation purpose, which is separating the P and N sides. Now we move on to the notation. You can observe here a plus sign with a circle over it followed by a small dot is shown. It represents donor atom with excess electron, which is basically electrically neutral. And this positive ion without that dot represents donor ion, which is basically positively charged. And that small dot at the bottom represents excess electron. Probably you may get wondered as why a positive sign is shown. The reason is this donor atom, which is basically electrically neutral, after donating one excess electron, it is going to become positive ion, and hence initially a positive symbol is shown over there. Donor atom means a pentavalent atom. Pentavalent atom means an atom having 5 electrons in its valence shell. Now coming to this notation, that represents an acceptor atom with excess hole, which is basically electrically neutral. And if this small circle is not shown, it becomes an acceptor ion, which is basically negatively charged. And that small circle represents an excess hole. Now, acceptor atom means trivalent atom. that is an atom having 3 electrons in its valence shell. This is the notation going to be used in the complete of this discussion. This notation is shown here. This notation will come in the next coming diagrams. Now, this Nd and Na stand for donor and acceptor concentrations, which are expressed as per centimeter cube. Assume Nd is equal to 10 power 20. Then the meaning is, if it is a silicon material, then per centimeter cube of silicon material, 10 power 20 donors are added to the right side, and 10 power 20 acceptors are added to the left side, making it N and P. That is the meaning of Nd and Na, called donor and acceptor concentrations, that is per centimeter cube. Now, the general doping concentration of this PN diode is 1:10 power 8. That is, I'll take an example. Assume that we are considering an silicon material, intrinsic silicon material. Then for every 10 to the power of 8 silicon atoms, if one donor atom is added to N side and one acceptor atom is added to P side, then the doping is called as 1:10 power 8. Now, if the base material is silicon, it is called as silicon diode. If the base material is germanium, it is called germanium diode. There are 2 types of diodes, that is silicon and germanium. Irrespective of which type of pentavalent atom is added or which type of trivalent atom is added to N and P sides respectively, still then the diode are only 2 types, that is silicon and germanium. So, if in general, if the doping ratio is 1:10 power 8, it is called as PN diode. As I said earlier, as doping concentration increases, the same PN junction could be called as Zener diode or tunnel diode. Out of this PN, Zener and tunnel diode is heavily doped, also called as degenerate. Now, coming to the construction, there are 2 types, namely step junction diode and linear junction diode. Let us see the difference. As I said earlier, this central dotted line is an imaginary line drawn for explanation purpose. Throughout the length of this N side, if doping concentration is constant and is equal to Nd, similarly, throughout the length of P side, if doping concentration is constant and is equal to Na, then it is called as a step junction diode. That is, exactly at the center, acceptor concentration will change to donor concentration. Whereas coming to the linear junction diode, doping concentration is different. That is, in this N side, as we move from center to the right or right to the center, doping concentration either linearly increases or linearly decreases. Similarly, in the complete of P side, from the center as we move to the left or from the left as we move to the center, as the length changes, doping concentration, that is acceptor concentration, either increases or decreases. That is, depending on the location or depending on the distance, doping concentration will be different in both P and N sides. That is what is called as linear junction diode. So these are 2 different types of diodes based on the doping concentration, called as step junction diode and linear junction diode. Now we move on to something called as NP0 and PN0. Some explanation is required for this NP0 and PN0. Now, when we are looking at this diode, it is being considered at room temperature, So due to room temperature, in the complete of this PN diode, electron hole pair generation will occur. That is due to temperature, that is room temperature. Now P stands for hole concentration. This P stands for hole concentration. PN, P suffix N means hole concentration in N side. Assume in this N side, due to room temperature, electron hole pair generation has occurred. It gives electrons and also holes. In this N side, already we are having electrons. Which are given by the donor atoms or impurities. So in this N side, we get electrons due to two reasons. One is electrons given by donor atoms, and the other is electrons given by electron hole pair generation. And in the same N side, we get holes due to only one reason, that is electron hole pair generation. That EHP generation will occur due to room temperature. EHP generation means an electron moves from valence band to conduction band. To go to conduction band, it needs an energy equal to Eg, that is energy band gap. And that Eg, energy band gap, amount of energy is given by room temperature. So now this P suffix N means hole concentration in N side. Definitely it should be minority concentration. Why? Because in N side, electrons are majority carriers and holes are minority carriers. Not means initial. That is, by the time we consider this diode for explanation purpose, already electron hole pair generation has occurred and PN0 holes are existing and hence called initial. Similarly, in P side also electron hole pair generation occurs due to room temperature. In P side, we get holes due to impurity atoms and holes due to EHP generation. In P side, we get electrons only due to EHP generation. So now N means electron concentration. NP means electron concentration in P side, that is minority concentration. Not means initial. So this NP0 and PN0 is called as initial thermally generated minority carrier concentration. Per centimeter cube is the unit. Here, coming to the notation, once you see this notation, you can understand as what is meant by these carriers. Why it is called initial? Just now I stated, it is carrier concentration which are generated already by the time we started the explanation, which is due to room temperature and hence called initial. Thermally generated, meaning is it is generated due to temperature. Which temperature? That is room temperature. And basically minority carriers. Holes in N side and electrons in P side, both are minority carriers. Now if you read the complete name, you will understand as how these concentrations are named. Initial thermally generated minority carrier concentration. So that is the meaning of NP0 and PN0. See, in our subject EDC, electron device and circuits, understanding the meaning of the notation is very, very important. What I suggest to any student is never by heart any notation. Everything will have a meaning. Try to remember with the meaning. Even the notations what we are going to write will have a standard format. D is the first alphabet in the donors, and A is the first alphabet in acceptors. So that is how ND and NA has been named. Now this is looking like a 3D view. Length, width, height, all the three dimensions are shown, called as 3D. But in the future we need to draw multiple times such type of diagrams. So to take care of the easy method of representation such that a student can easily understand, from now onwards I'll show you a 2D view of the same notation. That is, if you see the frontal view of this, it looks like this. I am showing the length and also the height. The depth part I am not showing, so that we can easily understand the concept. So from now onwards, instead of this 3D view, we will be using this 2D view. Now, if you look at this N side, what are the carriers existing? Electrons and also holes. If you say electrons are majority carriers, definitely holes will be called minority carriers. Why? Because electrons are generated due to EHP generation and also given by impurity atoms, whereas holes are generated only due to electron hole pair generation. So in N side, electrons are majority carriers, holes are minority carriers. In P side, holes are majority carriers, electrons are minority carriers. And we know a concept called as diffusion. In general, there are two types of motion for a charged particle. One is diffusion, the other is drift. This diffusion, what it says is, whenever there is difference in concentration of charge carriers move from higher to lower concentrated area, from higher concentrated area to lower concentrated area until uniform carrier concentration is achieved. For example, in this PN diode, to the right side we have more number of electrons, to the left side, P side, we have less number of electrons, and hence electrons should diffuse from N to P. In P side we have more number of holes, in N side we have less number of holes, and hence holes should diffuse from P to N. That is what is called as diffusion. So whenever there is difference in concentration, diffusion of charge carriers will occur from higher to lower concentrated area, ideally until uniform carrier concentration is achieved. That is, until throughout the length of the device, same number of electrons and holes are existing. That is the ideal situation, but it will not occur. Why uniform concentration will not occur? We will see in the next steps. Now, electron of N side has diffused to P side. You can see a violet color arrow is being shown. Similarly, hole of P side is diffusing to N side. Why? Because here electrons are less and here holes are less. Now, when this electron diffuses to P side, this electron recombines with this hole, and that is what is called as electron hole pair recombination. It is called as electron hole pair recombination. During EHP recombination, we lose one electron and one hole. Similarly, this hole recombines with this electron. It is also called EHP recombination. So due to diffusion, electron hole pair recombination will occur. Let us see what happens to the internal structure of the device. Now, if you can observe here, if you can observe here, all these atoms are donor atoms with excess electron, which are basically neutral, Due to electron hole pair recombination, they have lost electrons. And hence they have become positive ions. That is what is shown here. Similarly, all these atoms are acceptor atoms with excess holes, which are basically electrically neutral. Due to EHP recombination, they have lost holes. And hence all of them have now become negative ions. So can we now say that due to diffusion, electron hole pair recombination has occurred, and at the center some positive and negative ions got created. So due to difference in concentration, diffusion process has started, and these neutral donor atoms have become positive ions. These neutral acceptor atoms have become negative ions, and hence at the center we can state that positive and negative ions got created. Now if you can look at this diagram, in this area still electron concentration is less than n side. In this area still hole concentration is less than p side. Means throughout the length same number of electrons and holes, that is uniform carrier concentration is not yet achieved. So according to the phenomena of diffusion, still diffusion of charge carriers should continue. So this electron of n side diffuses to p, and this hole diffuses to n. Here one thing is to be observed. This is negatively charged acceptor ion. It repels this electron's diffusion. Why? Because this electron is also negatively charged and this ion is also negatively charged. Similarly, this positively charged donor ion repels diffusion of this hole. Why? Because this hole is positively charged and this ion is also positively charged. That is second level of diffusion. Second level of diffusion gets opposed by these positive and negative ions. From where we got these positive and negative ions? They got created due to EHP recombination. Why did EHP recombination occur? It is because of the diffusion. Of which level? The first level. So we can now state that previous diffusion opposes present diffusion. I can state that previous diffusion opposes present diffusion. That is, the first level of diffusion has created some positive and negative ions due to EHP recombination, where these ions will oppose the second level of diffusion, and hence diffusion may come to a halt. You can see this second electron's diffusion is opposed by this negative acceptor ion. This second hole's diffusion is opposed by this positively charged donor ion. This here we had an electron earlier, it could be called as electron number 1, then this is electron number 2. Here we had one hole earlier, it could be called as hole number 1, this could be called as hole number 2. That is, second level of diffusion gets opposed by the central positive and negative ions, and hence diffusion comes to a halt. Ideally speaking, diffusion of charge carriers should continue until throughout the length of the device same concentration is existing. Uniform carrier concentration is existing. But if you look at this diagram, in this area, hole concentration is less than this area. Similarly, in this area, electron concentration is less than this area. Still, diffusion has come to a halt. Why? Because the central positive and negative ions are opposing the diffusion. So initially diffusion has started, hence electron hole pair recombination has occurred, hence positive and negative ions got created which oppose the second level of diffusion. So diffusion starts and then comes to a halt, though uniform carrier concentration is not achieved. So as diffusion continues, opposition for further diffusion increases. Hence at some time diffusion comes to a halt. Now this central positive and negative ions, are opposing diffusion and hence given the name barrier. Remember that this barrier is a normal English word which means an obstacle. So this central positive and negative ions are opposing diffusion, are stopping the second level of diffusion, and hence these ions or this area is given the name barrier. So due to formation of barrier, diffusion comes to a halt. Now this barrier has some different names. We'll look at them one by one. You can observe here in this diagram some voluminous notations are given, and none of these notations need to be by hearted. I'll explain them one by one. You can observe here some dotted green lines are shown. Within those dotted green lines we have positive and negative ions. To the right side of this dotted green line we have neutral donor atoms. To the left side of this green dotted line we have neutral acceptor atoms. This central dotted line is an imaginary line which was shown earlier only for explanation purpose. So this area between the two dotted green lines is what we call as barrier. Now we will look at the notation of each of these things one by one. Now this positive and this positive is donor ions. They cannot move. This negative and this negative are acceptor ions. Acceptor ions, they cannot move. And hence this central area is having immobile ions. II stands for what? Immobile ions. What can move? Electron and hole. Electron and hole or charge carriers can move, but ions cannot move, and hence the central area is said to have immobile ions. This central area already is called as barrier, that you know. Why? Because it is stopping the diffusion process, and hence this central area is called barrier. And this central area is also called depletion region or depleted region. In depletion means in English not existing. What is not existing in this area? Electrons and holes, charge carriers. Why are we so much interested? In these electrons and holes, the so-called charge carriers? Why are we commenting on them so specifically that they are not existing? The reason is they support current. Current by definition is dq by dt. If a charge carrier moves through a unit cross-sectional area, then per unit time it can produce current. So in this area we do not have charge carriers, electrons or holes. They are only immobile ions, and hence given the name depleted or depletion region. Now, as I said earlier, this is positive charges, whereas this is the negative charges. This complete area is having neutral donor atoms. This complete area is having neutral acceptor atoms. So only this central area is having charges. Rest of it is neutral and hence given the name space charge region. Space charge region, because this is the only region in which charges are existing. Rest of the regions is having neutral atoms. And this central part is also given the name transition region. Transition means change of state. Change of state is what is called as transition. So from neutral we are coming to charged area. From charged area again we are moving to neutral area. So this is neutral area, this is charged area, this is neutral area, and hence the central part is given the name transition. Transition means change of state. So this is given the name transition region. And the central part is also given the name junction. Here, so in total this central area is given 5 different names, namely barrier, depletion region, space charge region, transition region or junction. So it has 5 different names. It is having II, that is immobile ions. Now, if you assume the central dotted line as origin, then to the left side and to the right side we have some distance. That complete distance is called W, that is width of depletion region. This W is called width of depletion region. It is written as something W is very much less than L. What is this L? Length of diode. So when compared to length of diode, this W is very small. See in this diagram, it gives an illusion as if W is 20% of size of diode. It is not real. W is very less when compared to length of the device. See, this area has been exaggerated. This central part has been exaggerated. Why? Because most of the explanation lies inside this barrier or depletion region, and hence this central part has been exaggerated in this diagram. But remember that physical size of this barrier is very less compared to length of the device or size of the device. And this is called Xn0, penetration of depletion region into N side. This distance is called Xn0, penetration of depletion region into N side. And minus Xp0 is called as penetration of depletion region into P side. As I said earlier, if the central dotted line, imaginary line, is assumed as origin, to the left side negative, to the right side positive. So from this diagram, W comes out as Xn0 minus of minus Xp0, which is equal to Xn0 plus Xp0, where the W is called as width of depletion region. Now we come to the next notation. See, if you look at this, actually we have a positively charged donor ion, but due to excess electron it has become neutral. And hence called neutralized ion. Similarly, here we have negatively charged acceptor atom, but due to excess hole it has become neutral and hence called neutralized ion. So these are not ions, they are atoms, and hence called neutralized ion. Neutralized ion means basically an atom. And the central area is having positive ions and negative ions, and hence called unneutralized ions. Unneutralized ions. Next, this positively charged donor ion is covered with a negatively charged electron, and hence it has become neutral, so called as covered charges. Covered charges. Similarly, this negatively charged acceptor ion is covered by a positively charged hole. Positively charged hole, and hence called covered charges. Covered charges. Whereas in the central area, that excess electron and excess hole are not existing. What happened to them? They are lost due to EHP recombination. Why recombination occurred? Due to diffusion. And hence the central area is said to have uncovered charges. Uncovered charges. So this is the notation which is being used in this diagrams. Now let me see whether there are any queries by the student. Okay. We will continue the discussion. A statement is given here: barrier opposes flow of majority carriers and supports flow of minority carriers. It's a very, 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 very important statement. Let us see the meaning of that. If you look at this electron, it is majority carrier of N side. Its diffusion is opposed by this negative ion. If you can observe, this negative ion is existing in the barrier. Similarly, if you look at this hole, it is majority carrier in P side. Its diffusion is opposed by this positive ion, which is in the barrier. So this central barrier is opposing flow of this electron, which is majority carrier in N side, and opposing flow of this hole, which is majority carrier in P side. So that is the meaning of this statement: barrier opposes flow of majority carriers. Barrier opposes flow of majority carriers. Hope I am clear. Now, fine. Let us see this supports flow of, this barrier is supporting flow of minority carriers. To understand the meaning of this, first of all, I am showing you minority carriers in the depletion region. Look here, this electron in P side is a minority carrier. This hole in N side is a minority carrier. If you can recall, what is meant by DR? Depleted region or depletion region. As I said earlier, what is the meaning of DR? It should not have charge carriers. It should not have charge carriers. Then, how can I show electron and hole again here? Definitely, it's a question to be answered. When we stated depletion region, we said charge carriers are not existing. But again, we are now showing charge carriers. Yes, it need to be understood. When I use the word depletion region, the meaning is it is depleted of majority carrier. It is depleted of majority carrier, but not minority carrier. Let us see the meaning. This hole in N side, if you can recall, it is called as PN naught. PN naught, hole concentration in N side. What is the name? Initial thermally generated minority carrier concentration. So in N side, electron hole pair generation will occur. So in the complete of n side, we have both electrons and also holes. How are they generated? Due to temperature. In this depletion region, how much is the temperature? Same as room temperature. See, throughout the length of the device, temperature is the same, equal to room temperature. So in this area and in this area also, due to electron hole pair generation, due to temperature, electrons and holes will be generated. No doubt in that, will be generated. Now, when I show this hole, it is generated due to temperature. So, a hole, a minority carrier can exist in n side, though it is depleted region. Why? Because depleted region means depleted of majority carrier. We cannot deplete minority carrier. If you want to deplete minority carrier, room temperature should be made 0. That is, electron hole pair generation should not occur. That is possible only if temperature is decreased. Similarly, this electron in p side is minority carrier. If you can recall, I said NP naught, initial thermally generated minority carrier concentration. So this electron and this hole are shown in depletion region, which are charge carriers generated due to temperature. They can exist, though it is depletion region. Now, in p side, holes cannot exist because they are maturity carriers. In n side, in the depletion region, electrons cannot exist because they are maturity carriers. Hope now you understand the meaning of depletion region. Depleted means depleted of majority carrier, not minority carrier. So this electron and this hole can exist, though it is depletion region. Now, this electron which is negatively charged gets attracted by this positively charged donor ion, and this hole which is positively charged gets attracted by this negatively charged ion. If you can recall, this hole and this electron are minority carriers. They are attracted by this positive ion and negative ion existing in the depletion region. So that is the meaning of the second statement. Barrier supports flow of minority carriers. So the ions existing inside the barrier are supporting the flow of minority carriers, but they are opposing the flow of majority carriers. So that is the meaning of the complete statement. Barrier opposes flow of majority carriers and supports flow of minority carriers. This is the meaning of the complete of statement. Now, this electron is diffusing to p side, which is a majority carrier. This hole is diffusing to n side, which is a majority carrier. That is the meaning. Majority carriers give diffusion current. This electron is moving to the n side and this hole is moving to p side due to the attraction exerted by this positive and negative ion. If a charge carrier moves due to difference in concentration, it is said to be diffusion. If a charge carrier moves due to attraction or repulsion of a potential, it is called as drift. How potential comes into picture, I'll explain later. As on now, solid violet color arrow represents diffusion. Repeating, solid violet color arrow represents diffusion. Dotted red color arrow represents drift. So minority carriers are drifting, majority carriers are diffusing. Now, this electron is diffusing from N to P. N to P, and hence it produces a current from P to N called as electron diffusion. Direction is P to N. This hole is diffusing to N side. This hole is diffusing to N side, and hence it gives a current called hole diffusion. Direction is P to N. Direction is P to N. Next, this electron is drifting from P to N. This electron is drifting from P to N, and hence it gives a current from N to P. N to P called electron drift. Electron drift. And this hole is drifting from N to P. Is drifting from N to P, and hence it gives a current from N to P. Solid line represents diffusion. This dotted arrow represents drift. Solid arrow represents what? Diffusion. Dotted represents drift. So in total we can say that there are 4 currents, namely electron diffusion, hole diffusion, electron drift, and hole drift. If you can observe at this arrow directions, we can easily understand that drift current opposes diffusion current. Diffusion current is from P to N. Drift current is from N to P. Or diffusion current is from, say, left to right. Then drift current is from right to left. So drift current is opposing diffusion current. Now, if diffusion starts, then electron hole pair recombination occurs. Immobile ions get created which attract minority carriers and hence give drift current. So due to diffusion, initially EHP recombination and positive and negative ions got created which attracted minority carriers and gave rise to drift current. So drift current has originated due to these ions which got created due to EHP recombination, which was due to the initial level of diffusion. So due to initial diffusion, electron hole pair recombination has occurred which has created ions, and those ions have attracted minority carriers and gave rise to drift current. Now, as long as diffusion continues, drift goes on, increases. Let us see the meaning. See, if diffusion continues, electron hole pair recombination occurs and central positive and negative ions get created which attract minority carriers and give rise to drift current. But this drift current and diffusion current are opposite in direction. So assume that initially drift is 0. That is, initially diffusion has not yet started, then diffusion is 0. Drift is 0 and say diffusion has started. Once diffusion starts, electron hole pair recombination occurs. Positive and negative ions get created at the center which attract minority carriers and give drift current. So initially drift was 0, diffusion has started and drift has come into existence. Assume that this drift in magnitude is less than diffusion. Already we stated that drift is opposing diffusion. Initially say drift is less than diffusion, just assume. Then diffusion will continue. Hence again electron hole pair recombination occurs. Hence more positive and more negative ions get created which attract more minority carriers and increase drift current. So as long as drift is less than diffusion, diffusion continues. As long as diffusion continues, EHP recombination occurs. More and more ions get created and hence increase drift current. So as long as drift is less than diffusion, diffusion continues. As long as diffusion continues, drift goes on, increases. At some time, drift and diffusion will become equal in magnitude. equal in magnitude, but since opposite in direction, net current becomes 0. Net current becomes 0 means diffusion comes to a halt. Diffusion comes to a halt. See, I stated that in explanation number 1, due to diffusion, ions got created which oppose the next level of diffusion, and hence diffusion comes to a halt. Though throughout the length of the device, uniform carrier concentration is not achieved. That is explanation number 1. Explanation number 2 is, due to these ions, drift current gets generated which opposes diffusion, and hence at some time diffusion should come to a halt. Why? Because it gets opposed by drift. So this is the second explanation. In both explanations, we are stating that initially in an open circuited diode, once the diode is created, diffusion starts, and after some time diffusion comes to a halt because of formation of central barrier. Now, just now I stated that this diffusion is, drift is existing. For existence of drift, definitely some voltage or electric field is required for us. Now, okay, this diagram got overlapped. Across these positive and negative ions, internally electric flux lines will get induced. Across these positive and negative ions, internally electric flux lines will get induced, and hence an electric field E0 gets generated. Whenever there is an electric field, automatically we get a potential V0. It is this V0 or E0 which is responsible for the drift current. I stated that V0 and E0 are induced. There is a meaning of this word induced. Induced means internally generated. Applied means externally initiated or externally triggered or externally connected. We are discussing an open circuited device, means there is no application of external potential to the device, and hence this V0 and E0 are generated internally and hence called induced. That is, across these positive and negative ends, internally electric field or voltage got induced, and it is this V0 and E0 which is responsible for drift current. Now this diagram is for without barrier and this diagram is with barrier. So when we consider an open circuited diode, assume that just then this doping process got completed, then it looks in this fashion. The very next moment it looks in this fashion. So any practical diode in this world is of type with barrier only. So this is how barrier formation occur in an open circuited diode. Okay. Before we move on to the next topic, let me see whether any doubts have been raised by the students in the chat box. Okay. We'll continue the discussion. Total negative charges lost in depletion region of N side is equal to total positive charges lost in the depletion region of P side. Let us see the meaning of this statement. Now, this is the depletion region of N side. And this is the depletion region of P side. I am showing the previous slide again. This is the depletion region of N side and this is the depletion region of P side. Suppose we lose say 100 electrons in this area, then we will lose 100 holes in this area. Why? Because it is electron hole pair recombination. That is the meaning of the statement. Total negative charges lost in the depletion region of N side, that is total electrons lost in the depletion region of N side, is equal to total positive charges lost in the depletion region of P side. Number of negative charges lost should be equal to number of positive charges lost, since it is electron hole pair recombination. Now for that I just want to derive a small equation based on the previous statement. Now here we have something called as ND. ND, as I stated, that donor concentration, that is number of donor atoms added per centimeter cube. Number of donor atoms added per centimeter cube. So it is number of donors added per centimeter cube. That is what is called as ND. Now a donor atom is a pentavalent atom. A pentavalent atom will have one excess electron. It has a total of 5 electrons. With respect to silicon atom or germanium atom, it has one excess electron. So each donor atom can give you one excess electron. So that ND I can write as electrons per centimeter cube. I can write as excess electrons per, or 1 electron per centimeter cube. Actually each donor equal to 1 excess electron. Now Xn naught is penetration of depletion region into N side. The unit could be centimeter. A cross-sectional area of this diode, the unit could be centimeter square. The unit is centimeter square. Q is charge of electron. The unit is coulomb per electron. If you cancel out, what is that we are left with? Coulomb. That is unit of this complete term. Is coulomb. That is total negative charges lost in the depletion region of N side. Is given by this, called ND Xn0 AQ. So this is the depletion region of N side. Total negative charges lost in this area is given by this equation. Similarly, this is the depletion region of P side. We have lost holes there. So if you want to know total positive charges lost in the depletion region of P side, we can write a similar equation, that is Na xp0 AQ. Just now I gave a statement that total negative charges lost in the depletion region of N side should be equal to total positive charges lost in the depletion region of P side, since it is electron hole pair recombination, and hence these two terms are equated. Now if you cancel out the common terms, we are left with ND Xn0 equal to Na xp0. A cross-sectional area, Q charge of electron and hole are equal. As we know, electrons and holes have equal magnitude, but the sign is opposite. So AQ gets cancelled. We are left with ND Xn0 equal to NaXp0. Nd and Na donor and acceptor concentrations. Xn0 and Xp0 is penetration of depletion region into N side and P side. Now already we gave one equation called W equal to Xn0 plus Xp0. We have an equation called W equal to Xn0 plus Xp0. Just now we have derived Nd Xn0 equal to Na Xp0. Using these two equations, we can derive two more equations. That is equation for Xp0 and Xn0. What is Xp0? Penetration of depletion region into P side. What is Xn0? Penetration of depletion region into N side. W is width of depletion region. Nd and Na are donor and acceptor concentrations. That is, using these two equations, we can derive these two equations. These equations could be useful while solving numericals. Depletion region penetrates equally into N and P sides for equal dopings, and it penetrates unequally for unequal dopings. This statement needs some small explanation. We have derived the equation of NdXn0 equal to NaXp0. Nd is equal to Na, that is donor concentration of N side and acceptor concentration of P side. Assume they are equal in magnitude. They are equal in magnitude. Then Nd and Na gets cancelled. We are left with Xn0 equal to Xp0. That is, if doping concentration of N side and P side are equal, then penetration of depletion region into N side and P side will also be equal. That is observed in this diagram. From 0 to Xn0, distance will be same as 0 to minus Xp0. Since we assumed this as origin, that minus sign is shown there. So modulus of Xn0 and modulus of Xp0 should be equal. That is, depletion region penetrates equally into N and P sides for equal dopings. We will see the meaning of the second half of the statement. Nd is not equal to Na. That is, donor and acceptor concentrations are not equal. Just assume. Then from this equation, Xn0 should not be equal to Xp0. That is, penetration of N side and P side will not be equal. Will not be equal since dopings are not equal. That's what is observed here. Do you observe that Xn0 is more when compared to Xp0? Yes. That is, this diagram has been drawn under the assumption that Nd and Na are not equal. That is, donor concentration and acceptor concentrations are not equal is assumed while drawing this diagram, and hence penetration of depletion region into N side and P side will not be equal. Depletion region penetrates more into lightly doped side. Let us see the meaning of this statement. I am assuming that Na is greater than Nd. That is, in this equation, acceptor concentration is more when compared to donor concentration. Now, to sustain equality, Xn0 should be more than Xp0. See, in the right hand side, Na is more compared to Nd, but equality should be sustained. So to get this equality, we should definitely increase Xn0. So Xn0 should be greater than Xp0. Now what is Xn0? Penetration of depletion region into N side. And what is doping in N side? Nd. Is it less than Na? Yes. So whole concentration is more, whole doping is more when compared to electron doping. That is, N side is doped less. And into that N side, penetration is more. That is the meaning of this statement. Depletion region penetrates more into lightly doped side. Depletion region penetrates more into lightly doped side. So we are assuming that ND is less than NA and hence Xn naught is greater than Xp naught. This statement is very important. Why? Because based on this statement, we explain plenty of concepts in plenty of devices. If you can recall in a BJT, bipolar junction transistor, when collector junction is reverse biased, depletion region penetrates more into base when compared to collector. Why? Because out of this collector junction diode, collector is doped more than base, means base is slightly doped and hence depletion region penetrates more into base, and that is given the name punch through, and the concept is given the name early effect. So in early effect, we will be using this statement. Similarly, in JFET, junction field effect transistor, you know something called as pinch off. When the top and bottom gate junction diodes are reverse biased, assume that it is a n-channel JFET. Top and bottom we have P plus gate. That P plus gate and n channel, if it is reverse biased, depletion region penetrates more into channel. Why? Because that channel n side is slightly doped when compared to P plus side. So that concept of pinch off is again explained using this statement. So though we are discussing a concept here, it will be used in some other devices. Thus what I stated at the start of the discussion, understanding the operation of PN diode is very important. Why? Because once you understand this, you can easily understand the operation of any other electronic device. Now we move on to something called as circuit symbol. A circuit symbol should identify the number of terminals and also the names of terminals. A circuit symbol of any device should identify the number of terminals and also the names of terminals. By looking at this circuit symbol, can we say that it is having two terminals? Yes. Vertical line represents N. Triangular piece represents P. So this circuit symbol is able to identify the number of terminals and also the names of terminals. That is the primary information to be given by any circuit symbol. Now, in this circuit symbol, that arrow shows direction of flow of current when the diode is forward biased. This arrow shows direction of flow of current when the diode is forward biased. When the diode is forward biased, we know that current goes from P to N. And hence the arrow is pointing from P to N. Remember that a circuit symbol is used to minimize the size of any device and to give you all the basic information for ease in understanding. Now, before the existence of this PN diode, we had something called as vacuum diode. This vacuum diode or tube version of the device is a glass structure, internally vacuum. It has two thick connecting wires called as anode and cathode, that is electrodes, anode and cathode called as electrodes. This was the original version of this device which we are using now. This is called as solid state diode. This is called as vacuum diode. Initially, long back, we were using only vacuum diodes. If you can recall, the first ever found computer in the world, ENIAC or UNIVAC, was made up of such type of vacuum devices which are large in size. they have more power consumption, operation is completely temperature sensitive, whatnot. It has plenty of disadvantages. So nowadays we are not using those vacuum versions. Instead, we are using equivalent solid state devices. So this vacuum device is having two electrodes called as anode and cathode. Anode and cathode, and hence this device is given the name diode. Diode. Di in English means two. OD is a part of electrode. OD is a part of electrode. So to remember the first ever device, to remember the first ever found device called as vacuum diode, this is given the name diode. Diode. In this diode, we have one p-type material, one n-type material, and hence called PN diode. And hence called PN diode. Just now I stated that at the center a junction is forming. A junction is forming, and hence given the name PN junction diode. And hence given the name PN junction diode. So if you can recall, even the name has been given in such a way that you can easily recall the name. So the nomenclature or the naming or the notation can be easily remembered based on the concept behind it. Initially, I was stating about PN naught and NP naught. It was given the name initial thermally generated minority carrier concentration. Initial, why? Because it was existing by the time we started the explanation. Thermally generated, why? Because it is generated due to temperature, room temperature. So in the complete of our subject, electronic devices and circuits, never by heart a notation. Try to see as what is the logic behind it. If you can see, even the name of the device need not be by hearted. It can be easily remembered based on how it was found. Let me see whether there are any doubts in the session. Okay, there are no doubts in this session. So as on now, we have completed the formation of barrier in an open circuited PN diode. If any students have future any doubts, please post in the chat box. I'll respond to you. Okay, and I request all the students to please subscribe for ACE YouTube channel. Thank you. We'll meet in the next session.